Today we're going to continue what we've started in the last lecture. We started to study dynamic formulations, and in particular what we've been doing is to derive what we call the AV, magnetodynamic formulation. And so this formulation, we established it in terms of two potentials. So the magnetic vector potential, A, and the electric scalar potential, V. And so these two were coupled in the formulation. And if you remember what we did, we derived this formulation in a very general setting, so in 3 dimensions. And in addition to deriving the weak form, we also thought about how to couple it with global quantities. So in our case, for magnetodynamics, currents, so current intensities, the global current, and then the global voltage. And so the way we did that was very similar to the way we did it for electrostatics or electrokinetics or magnetostatics. We assumed for magnetodynamics that we had electrodes on which we would have a constant scalar potential V. And on these electrodes, we would have this term over here in the second equation when the V prime test function is chosen to correspond to the test function on the electrode. You remember with the summation of the nodal function that sum up to 1 on the electrode? Well, this term over here is the integral of n dot j dotted with V prime. In this case, V prime is equal to 1. And we have this term that would lead to the global current intensity, right, in amperes. And V would be the voltage. So we derived this magnetodynamic formulation in the general setting in 3D, and then we finished the lecture by looking at what happened in a particular case when we had a system invariant along one direction. So conventionally we used the invariance along Z, and then we looked at a 2D simplified formulation in the cross-section, in the XY plane. And we saw that you could apply it directly with A, now a vector that would stick out of the plane. And so basically what we had was extremely similar to what we derived for magnetostatics, except that now we could take dynamic effect into account. And so if we go back to the equations and we look at the terms, you see that you have 2 terms. So one over here and one over there, where you have a time derivative, dt, over there and over there. And so that's the first time we have it. Okay, so what I want to do with you today is something very practical. I want to show you that the quite complicated equations that we derived last week, well, we can use them to solve actual problems. And this will lead us to actually your, let's say, next homework, where you're going to actually design a practical device, which is a dynamical device. And well, we'll learn about all of that in this lecture. Okay, so let's have a look at what we had in practice last week. So we had this weak form that looks a bit complicated, and what we looked at last week was the implementation of that in this template library file. And in this template, if you remember, what we did was to look line by line at all the terms that we have in the formulation. So in the lecture last week, we basically made sure that everything in here, if you remember, you have all these terms. The term here with the relativity times the curl of the vector potential, dotted with the curl of the test function. And then we have the term here with the remnant magnetic flux density in magnets. And then we have the term with the time derivative in the conducting regions, etc., all the way to the terms with the global quantities, currents and voltages. And so all of this we can take as granted today. We made sure last week that all the terms matched with the theory. And so what we're going to do today is just use this as a black box. And so for our black box, we need some inputs and outputs. And so what are the inputs? So what are the parameters? Well, if you look at the beginning of this template library file, you'll see that, well, I have 3 categories of let's say, parameters that I can set from the outside. So the idea is that this file, you can leave it as is. You could actually, well, almost forget, I would say, what we did last week. Well, don't, right? But you could almost forget what we learned last week and just use this library as a black box by basically defining these parameters that I will describe now. So we have some constants that will basically govern the way the library works. And then we have, on the one side, groups that we need to fill. Basically, the library is written in a very generic way in terms of abstract groups. And so these groups are empty. And so your goal when you want to solve a practical problem is to basically just fill these groups with, let's say, actual parts of the meshes that you've been generating to describe the geometrical model that you want to solve the problem on. And then you have functions. And so these functions basically describe material properties, or as we will see later on, the lumped circuit elements if you do circuit coupling. So we'll see that later. Okay, so what is the example that I want to play with first? Well, if we go back to the page for magnetodynamics, well, this is the first example we looked at last week because it's the same as the one that we studied for magnetostatics. So if you remember, you have an inductor in which we have a current flowing. We have a core. Contrary to magnetostatics, now we want to see the effect of eddy currents. So we suppose that the core was both magnetic and conducting. And so the current in the coil produces a magnetic flux density that turns around it. And here we see a reaction in the core, a dynamic reaction, due to the fact that we have eddy currents that take place. Okay, so let's have a look in detail at how we can solve this in dynamics. So it is in what is called the electromagnet.pro file. And so this is my example. You see that this is quite short. So, okay, 120 lines. And well, first thing you see that deep down in the file, well, we include the template. So we include this lib magnetodynamics 2D AV SIR. The SIR here is for circuit. And then what else? Well, we see that we also include here another file, electromagnet.common.pro. So maybe let's start with that. Let's have a look at what's in electromagnet_common.pro. Common.pro. Wow, there's almost nothing. So what's in there is the definition of the internal and external radius for the infinite region transformation, the annulus that we have around the geometry. We can maybe check that. So let's open the geometry, electromagnet.geo. We have this infinite region over here. The interior radius is 0.2. Here it's 0.25. And indeed, this is what we have here, 0.2, 0.25. All right, so what else? Okay, so we have the include, and then we have the groups. So now we are familiar with this. So we could just check, just to make sure that everything is correct. So I said that the air was region 101. And so let's have a look over here. Okay, air here is clearly physical surface 101, so fine. Core 102, indeed. Inductor 103, okay. And the infinite region 111, that's fine, great. What else? We define some surfaces. Well, in this 2D setting, these will be curves. So we have ht0, so meaning that the tangential component of h should be 0. So that's going to be 1,100. So where should that be? So tangential magnetic field equal to 0. If I impose a current here, my flux density is going to rotate like this. So it should be on this line over here that I have no tangential component. And indeed, 1100. What else? Bn0, so no normal flux density. So 1101, that should be over here, right? Indeed, it is 1101. And then this should be the infinite, let's say the curve modeling infinity, 1102, and that's it. Okay, so this is the link with my geometrical model. And now look at the way this template is defined. We basically fill the abstract regions that are defined in the template. So what are these regions? Let's go back to the template and let's have a look at what we need. So we need the full magnetic domain, and then we can define some subsets. So some can be empty. Over here we're going to have what? Well, clearly the core. Well, we're going to assume that it's a conductor. So vol C, we need to fill it. Stranded conductors with imposed current voltages circuit coupling. Okay, vol S, we need to fill that. We have no magnets, but we have an infinite region. Okay, so we're going to fill these regions. How do we do that? Well, as simple as that. Vol mag, okay, it's everything. The air, the core, the inductor, and the infinity. Conducting region, only the core. And the source, the inductor. Infinite region, air inf. And then we define these two parameters for the internal and external radius based on the stuff that we included from the common file. Okay, that's it for groups. What else do we need to do? Well, you remember in this template we have some constants. Let's have a look at the beginning. So the path of the model, we don't care. Okay, the default path is the current directory. The path for results, okay, we can leave it as is. So you see that there are default values for all these constants. Constants can be strings or floating point numbers. And you see here that we have some flags. So a flag for axis symmetry. So let's leave it to 0, which means that we look at a 2D problem. If we put it to 1, we're going to look at a problem that is axis symmetric. We can, this is important, change if we work in the frequency domain or in the time domain. And so we'll cover this in a few minutes. And so let's assume that we're going to leave it to the default value. So we're going to start with frequency domain analysis. And then we can decide if we do circuit coupling or not. Over here, if we just impose a current or a voltage, we don't need circuit coupling. This is going to be interesting in the second example that we're going to work on today, where we want to couple our dynamic model with an external circuit that involves, let's say, lumped circuit elements. So I'd like to have, let's say, an external circuit with voltage or current sources, resistances, inductances, capacitors that I could basically play with in order to couple my finite element model with an external circuit. So we'll need to put this to 1 in the second example. This is for nonlinear problems, so you can skip it today. The power coefficient, you'll skip it, so it's going to depend if we work with, let's say, maximum amplitudes of fields in the frequency domain, or if you look at RMS values. Frequency in the frequency domain. But then for time domain calculations, you'll see that we'll need to specify actually the time interval in which we solve our problem. So an initial time, a final time, and a time step. Here you can choose actually to do higher order finite element solutions. We'll leave it to 1. And then here you see the int rx values. The center of this infinite region is going to be 0, 0, 0. And then here some parameters for the nonlinear resolution. So what do we need to fix in our case? So let's look at what I did over here. So this is clear. So let's look at these functions. So I started by defining some additional constants actually that the user could modify. So U. Well, here I have the permeability of the core, the current intensity, a flag to say if we work in the time domain or in the frequency domain, and if we are not in the time domain, the actual frequency. So instead of looking just at the open, and what do we see? Well, we see that we have here the parameters that we just defined. So we have a choice between frequency and time domain, current, frequency. We have an additional parameter here, the global mesh size, and then the relative permeability of the core. Okay, so what do we need to do? Well, let's have a look. So we have our parameters here. Let's leave time domain to 0 for now. And so we're going to do the analysis in the frequency domain. So we ignore this block for now. And we look at what we have here. So you see that here I fix actually frequency domain to 1. I could have left the default value. It's the same. But then I fix frec to the frequency that I expose to the user over here. And then what else do we need? Well, let's go back to the library. We need some functions. So we need the relativity in volmag, the conductivity in the conducting part and in the source part. If we had a magnet, we'll need Br and blah, 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 all the rest. Important parameters are Ns. In the source region, you can specify the number of turns. So we're going to assume that we have a perfect stranded inductor. So an inductor made of many different turns in series, which means that we can make the hypothesis that the current density is going to be constant across the coil. And this is the number of turns. And of course, in order to link the total current and the current density, we'll need the cross-section of the windings. And this is the function SC. So we need to provide that. So let's see how we do it. We basically do it as we did in the previous examples. So here I define a constant for the permeability of vacuum. And then relativity everywhere is 1 over mu 0, except in the core, where it's 1 over the relative permeability of the core times mu 0. Conductivities are defined like this. And then here you see that we define the number of turns to be 1,000. So we have 1,000 turns in the coil. And the section, we use the function that we already saw in the magnetostatic case. We use this built-in function surface area that allows to use the mesh directly to compute the surface. We have our JS0, so the current density, which is the number of strands divided by SC times 0, 0, minus 1. So this is like our unit, the current density for unit current. And then we'll see that we'll multiply it with the actual current intensity, later on. And then we have this geometrical coefficient. In the 2D case, this will be the depth or the thickness of the model along the invariant direction. So in our case here, along Z. And so here I leave it to 1, so it's going to be all calculations for a 1 meter thick model. Okay. Well, that's it. So we have our groups. We have our functions. What else do we need? Well, we need to set up the problem with boundary conditions. So what are the boundary conditions that we're going to use? Well, this is exactly the same thing as we did in statics. So we'll impose that there is no normal flux on surface B and 0, and the same condition actually on the infinite surface, and this is made through the imposition of a Dirichlet boundary condition on the vector magnetic potential over here. So we set it to 0. And then here we can play with the global quantities. In this example, we're going to impose a current. So we impose the current in the inductor. And now we're working in this first test in the frequency domain. So I will impose in the region inductor that the current is current. And so what is current? If you remember, current is this constant that we make available in the user interface. Okay? We'll see later on actually that in the time domain you also need to specify how the current varies in time. We are not done because we have, if you remember, conducting regions. So we have the inductor, which is in vol S, and then we have the core, which is also conducting. So we need to specify either the voltage or the current. And so here I apply a constraint that tells me that in the core, actually my global voltage is 0. Okay, and then I include my library. And then I define some post-processing. And so here, very elementary, I define a post-processing to plot A, the magnetic flux density B, and the current density J. Okay, so that's it. So let's have a look. So if I run this test, this is what I get. So if I look at J, okay, J is here. But here you see I have a real part. And so now is the time to refresh your memory about what is a frequency domain approach to solving these time domain equations. Because we have, in effect here, a time domain formulation with time derivatives. So how did I do to solve this and obtain what are essentially complex fields? Right, I have J here, real part, if I look at sorry, the options for this view, so it's view number 2, you see that there are 2 steps actually in here. I see that I have a real part for J and then the imaginary part, which is 0 actually for the current density. What this means is that J is actually a phasor. So J is a field with a spatial dependency, but each spatial component actually has a real and an imaginary part. And so how did we go about to obtain this? So let's go back to the formulation that we had. And so what we did is the following. So in order to work in the frequency domain, we did 2 things. So first, we assumed that BR was 0 in such a way that we had no constant in time source term in the equations. And all the rest, we assume that all other quantities depend on time sinusoidally. So let's take a look at our, let's say, magnetic vector potential A. So A is a function of, in the general case, x, y, z, and t. What we suppose, in effect, is that I can write it like this. I can write it as A of x, y, z. I should use another letter. Maybe I could use a capital, maybe. Capital A of x, y, z times the cosine of omega t plus a phase that can also depend on the spatial location. So this is my hypothesis. Okay? So if A is a vector field that still depends on the position, but the time dependency, I can write it like this, then I can write it also like this, right? I can write it as the real part of what? Well, of my field A of x, y, z that multiplies e to the I omega t plus phi of x, y, z. And then what's the trick? Well, the trick is to separate the complex exponential. So this is the real part of A of x, y, z that multiplies e to the I phi of x, y, z times e to the I omega t. And this guy here, you see that it does not depend on time. So it's a pure spatial field, and we redefine it as a phasor. Maybe like this, or maybe I could put a little bar below, or there's no single notation. I could do it like this. So to say it's a complex number, a complex field. Okay? So it's the real part of this complex field A. So which has an amplitude and a phase term times e to omega t. Okay? And the trick is that this is actually the field that I need to compute, because if I look at my equations, imagine that I replace A over here, and I can do n over here with that expression. I do the same treatment for V. So remember, I remove this term. So I have V over here. Imagine that Js also I can express in the same way, and that J I can express it as well, and H as well, and V as well. So if all the quantities I can express them in the same way, so as a phasor field, so a complex field, times e to the I omega t, then I will be able to remove it and simplify all the e to the I omega t's. Because here I have an e to the I omega t that will come out. Here as well. Here it's going to be a bit different. I have a time derivative. If I take the time derivative of this guy, I will have I omega that comes out, but that's fine. So I will have I omega that comes out, and then I have the e to the I omega t that I will be able to take out of the integral as well. Here, same thing. Here, same thing. So I take that equation, I remove all the e to the I omega t. Well, I end up with what? I will end up with that equation where dt has been replaced by I omega. And that's it. And all my quantities will become phasors. Oh, I have whoops, sorry. I don't have BR. I said that I didn't have BR. And I have, okay, all these quantities here, that will become phasors with little bars. I have the same here. Here I have, again, with the time derivative, I'll have an I omega that appears. And then here I have a phasor, and here I have a phasor. So, in effect, it's extremely easy because the equations that we had are actually exactly the same, except that dt is replaced by I omega, and that the fields, we have to understand them now as complex valued fields. And this is precisely what we are doing in the formulation. If model, and I look at my library, actually the equations over here, you can write them once for all, provided that each time you see dt doff, and if you are in the frequency domain, well, you replace dt doff by I times the pulsation, I times omega. And so that's the reason why you can actually write the equations in the frequency domain or in the time domain a single time. You don't have to rewrite them. The thing that will make the difference is simply when we look at the resolution in the frequency domain, well, we need to say that the fields are not real valued fields that depend on time anymore. We'll say that the fields are complex valued fields. So these are these phasor fields. We only solve for that. We of course need to specify the frequency. The frequency is the stuff that is over here. Omega is 2 pi times the frequency. And why do we need to specify it? Because of the time derivatives. Right? Because of the time derivatives, you have these I omega terms that appear. GetDP does it for you. So every time it sees a dt doff, it will replace it by pure imaginary number I times the pulsation omega equal to 2 pi times frag. Okay? So GetDP is actually a bit more general than that. You could actually specify multiple frequencies, and these multiple frequencies, actually, you could couple them to write what we call harmonic balance formulations or multi-harmonic formulations. And so this actually would allow you to keep magnets, but we are not going to cover that. So you basically write then coupled system of equations that are directly exploiting, let's say, a Fourier series of all the fields, and you could keep the DC component and as many harmonics as you want. But in our case, we just keep one harmonic when you work in the frequency domain, and we suppose that everything varies according to this single harmonic. This, of course, is only valid in the linear case, because our assumption is that all the quantities can be written as this simple function of time, which is the real part of this complex exponential, so basically cosine in time with a variable phase shift. Okay, so that's the frequency domain solution. So it's extremely easy, and if you run the case, now you understand exactly what's happening. So let's run it. What I obtain for all the fields are phasor fields with a real part. So this is my magnetic vector potential. If I look at the imaginary part, you can just press on the right arrow. Well, this is the imaginary part. And you see here that you have a non-zero imaginary part. This is the dynamic effect. This is due to the fact that you have eddy currents in here. So let's have a look at B. So if I look at B, this is the real part, and this is the imaginary part. So you have real and imaginary part. If you wanted to look at the time evolution, it's easy, right? For any quantity that we have, if I have the phasor here, I can easily go back to the time domain. How? Well, I multiply with e to the I omega t, and I take the real part. Well, you have a little function in Gmesh that does this for you. You go to Tools, Plugins, and you have a plugin called harmonic to time. What does it do? It takes the real part, the imaginary part, it discretizes time over one period with a given number of steps, here 20, and then it basically creates a time domain animation of the field. So let's run it. And so this is what you get. And so if again I press on the right arrow to do my animation in time, so you see this is step 0 of 19, so we have 20 steps. And so if I do the animation, this is what I get. So if I leave my finger, I'm going to animate. And so here you see now what the time variation of B is. We see it quite clearly. We see that the induced effects, what we could do, look, we're going to animate both B and J at the same time. So let's also apply this plugin on J, so on view 2. And let's plot B and J. So we have the two, let's say, fields of interest over here. Let me make this a bit bigger. Okay. So let's animate everything. So what do we see? We see that we have clearly a regular sinusoidal variation in time of J. And you see the induced, well, the created magnetic flux density. And you see here the delay that we have here. We are solving a parabolic problem, so a problem with dissipation over here. And you see that you have a delay between the excitation and the way that this field is distributed in the core. If we just look at the current, depending on the values that we said, we should see eddy currents appearing in the core. They are quite small over here. So let me make maybe the arrows a bit bigger. So let's look at the options for that field over here. So we can go to aspect and then to increase the arrow size. And what you see, indeed, you have a little bit of eddy currents here. It's still very small. So the conductivity was quite small and the coupling is pretty bad, right? You have a large, let's say, air gap in here, but you see them now. Okay. And so you see that's phase shifted by 180 degrees. You see your eddy currents. So when my excitation current is going this way, the induced current go the other way with a phase shift. And you see here the eddy currents in the core. Okay. You also directly see skin effect. You see that eddy currents are concentrated in the periphery of the core. And this will depend on frequency. So if I redo the same calculation at 100 Hertz, we can redo this. Let's have a look. And we look at the induced currents. So same thing. Let's not go back to the... You see now that the currents are distributed closer to the boundary. This is basically a practical example of skin effect. Skin effect will depend on the permeability as well. So if I increase the permeability of the core and I redo the calculation, you'll see that things will concentrate even more in the so let's increase the size again. And you see here that the currents really, so the mesh is getting a bit coarse actually to represent the currents, but you see that everything is concentrating across, well, close to the border, to the boundary. Okay, so this is our first, let's say, example in the frequency domain. I encourage you to play with it because we're going to have in your homework, well, we're going to play with this model quite a bit, but we're going to introduce some additional things. I talked about it before. We'll need to actually introduce circuit coupling because this example is very simple because either we apply the current or the voltage. I would like to be able to play more and to actually include an external circuit to actually have more realistic sources and loads in the model. Magnet, and before doing these more complicated models, let's finish, let's say, this first part with this electromagnet example by looking at not the frequency domain analysis, but the time domain analysis. So we did frequency domain. We could do time domain. So conceptually, time domain is actually simpler than frequency domain. What do we do to do a time domain analysis? Well, we're going to keep time derivative, but we will discretize these time derivatives in time by approximating them through finite differences. And so we're going to say that the time derivative of a of x, y, z, t, well, I'm going to approximate it as a of x, y, z, t, let's say plus delta t, minus a x, y, z, t divided by delta t. Okay, so I do basically a finite difference approximation. You could do much more complicated schemes to discretize your equations in time, and so you know about all of that. You will learn about this in numerical analysis, and some of you with myself reviewed this last year in the applied math class. In the formulation, again, doesn't change anything. You leave the equations as they are. You leave the dt. You don't change that. But in the resolution now, the resolution becomes a bit more involved. Let's have a look. So frequency domain, we understood. You just generate, solve the system once, save the solution, and you said, okay, I know how to treat the derivatives because I use complex fields and I have the frequency. In the time domain, it's a bit different. You know, here you have first derivatives in time, so we'll need an initial condition. By default, the initial condition in getDP is that the field is equal to 0. If you wanted to include a different initial condition, you can. Let's skip that for now. And then we apply a time discretization scheme. And so what we do here is what is called the theta time scheme. And you know about this scheme because you learned about it. And over here, I specify the theta parameter to be 1, which leads me to do an implicit Euler time integration, the simplest, let's say, time integration scheme, which is unconditionally stable. So you can take extremely large time steps. Of course, if you want accuracy, you need to refine time, but you have no constraint on stability. And then what do we do? Well, you have this loop, which is pre-coded for you. So this time loop theta with theta equal 1. And you give parameters, the initial time, the final time, and the time step. And then at each time step, you do a generation of the system, and you solve the system. And that's it. If the problem was nonlinear, we'll talk about this in a future lecture. Actually, you will need to iterate. Whoops, 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 whoops. You need to iterate, and the iteration here can be done in two different ways. You can do either a Picard iteration or a Newton-Raphson iteration. We'll cover this in a lecture, an upcoming lecture. For now, everything is linear, so at each time instant, you generate, you solve, and then you also save the solution. And actually, that's it. So let's have a look at how this works. So let me close this and let's reopen the file. Frequency domain, let's solve in the time domain. So in order to understand what will happen, well, let's run it first, and then we'll have a look. So if I run it, well, you see that it's generated, solving, generating, solving, generating, solving. Okay, it's done. Here I did 21 time steps, or 20 time steps, I guess, with the initial solution being the first one, so step 0. If I look at the current density, so I just play the animation. Okay, the current increases, and then it stabilizes. Okay, do we have eddy currents? Let's have a look, maybe. Let's increase the scale a little bit for this guy. Up over here. Oh yes, we do. So let me start the animation again. Oh yeah, you see that during the transient, of course, I have eddy currents, and they point, well, let's do really large arrows. They point upwards. Okay, which is what we expected. So you see that the differences are minor. So this is our option, time domain 0. So let's have a look. Time domain 0, if time domain. So what do I need to do? Well, we need to fix flag frequency domain to 0 now. And we need to provide the three main parameters, the initial time, the final time, and then the time step. And so here I chose some parameters just to do a little demonstration. So we start at t equal to 0. We go all the way to t equal to 20 milliseconds. and we use a time step of 1 millisecond. And then, of course, we need to say how the excitation varies. So in this problem, remember, we impose the current, the total current, in the inductor. Well, if I was in the frequency domain, I just impose the maximum amplitude of the phasor. So in the frequency domain, if I go back, what I impose is this guy, but not for A, for the current, the global quantity. And in the time domain, well, I can impose that, but then I need to impose a time variation. And this is done with this time function, which here I call my modulation. So what I will impose is current times my modulation. And if I look at my modulation, I define a little function here. This is the first time you see it. In GetDP, you have the concept of runtime or current variables with dollar signs. And so these variables are updated at runtime when GetDP is running. So all the rest, if you read this, this is analyzed when you read the input file at the beginning, but this is not interpreted as the code runs. This is done statically once in the beginning. But the variables with a dollar, these are evaluated at runtime. And here, every time we do the time integration, so the time loop theta, at each time step, this variable will change. And so you can do tests like this. You can say, well, if time is smaller than half of my simulation time, right, time final divided by 2, then, so if this is true, then I will assign to my modulation this function here. So 2 divided by time final times time. Otherwise, I'll impose 1. And so what does that mean? Well, I have a linear ramp from 0 to 1. So let's draw it maybe. So if I look at my excitation I of t, well, I'll grow linearly, and then I'll stay constant. And this is, how did we call it? Time init, time final. So this is time init, and this is time final, and this is halfway. Okay, and that's it. Actually, you see, nothing else changes in the file. You basically impose your current like this, and you need to fix this flag to 0, and that's it. So that was our first practical example using the complicated formulation that we derived in the previous lecture. And so I'll stop here for this part. And in the next part, we're going to check out a slightly more complicated example where, in addition to everything we did here, we'll introduce some coupling with lumped circuit elements in order to be able to have more realistic sources and loads.